Equilibrium constants can be used to calculate the concentration of reactants or products if a system has reached equilibrium. In this example, we'll be using the dissolution reaction of calcium carbonate. So calcium carbonate solid dissociating to form calcium and carbonate ions in solution. In this problem, we're asked for the maximum calcium concentration. So we're trying to figure out the calcium concentration in a solution with a carbonate concentration of 3.7 times 10 to the negative 5 molar. And we're given a solubility product constant. Now that's the equilibrium constant for a dissolution reaction. So in this case, it's the products over the reactants. The reactants won't show up because it's a solid. So my products would be calcium 2 plus, the coefficient's 1, so I don't include an exponent, times the carbonate. And again, the coefficient is 1, so I don't need to include an exponent. And so basically, if we're given the KSP of 2.8 times 10 to the negative 9, and we have one of these concentrations, we can calculate the other. In this case, we're trying to calculate the calcium concentration, and I can do some simple algebra, dividing both sides by the carbonate concentration to get the solubility product constant over the carbonate concentration. And I can go ahead and plug these values that I was given into the equation of 2.8 times 10 to the negative 9. Now notice the KSP does not have units. Okay, and as I enter these concentrations, it's important that they're in units of molarity, but I'm not going to include the units. Now there's a fancy reason for this having to do with activity coefficients, which we're not getting into in this video, but it's important that this number be entered in units of molarity, but you don't carry the units through the calculation. And this gives 7.568 times 10 to the negative 5. Should have two significant figures. And when I'm calculating a concentration from an equilibrium constant, the concentration is going to come out in units of molarity. So I suppose if I had put molarity here, it would look like the units would be 1 over molar. That's not how it works. The concentrations that come out of these calculations will be in units of molarity. So this should be rewritten that the concentration of calcium in this solution, the highest you can get without it starting to precipitate, would be 7.6 times 10 to the negative 5 molar. Okay, let's do one other. This one's a little more complex. In this example, we're given a concentration, or we're given a solubility product constant, and we're asked to calculate both the calcium and the carbonate concentration. What's the molar concentration of that saturated solution? So the saturated solution is one bit that's important. That's saying it's come to equilibrium and as much of these ions as could dissolve have. And the other bit is implied in this question, is we're not given information about either calcium or carbonate being present in the solution before this began. So we're going to assume that we started with lots of this, no calcium or carbonate in solution, and that it was allowed to dissolve, and some amount of it, X, dissolved and formed calcium and carbonate. Now we need to pay attention to coefficients, and in this case, for each amount that drops of the calcium carbonate, 1 each of calcium and carbonate came in. I might have to have a 2x or a 3x if there were coefficients in the balanced chemical equation. And so if this was sort of what I had initially, this is how it's changing. When it reaches equilibrium, I'll still have lots of calcium carbonate, but I'll have the same concentration of calcium and carbonate ions. And that means that I can plug those X values into my equation for the solubility product constant, and I'll just get X times X, or the KSP will be equal to X squared. And this is easy to rearrange. X will be the square root of the KSP. or the square root of 2.8 times 10 to the negative 9, or 5.2915 times 10 to the negative 5 molar. And again, this should be two significant figures. So X, which is the concentration of calcium, or the concentration of carbonate, or the concentration of calcium carbonate together, will be equal to 5.3 times 10 to the negative 5 molar. Now I made assumptions here that I started with neither calcium nor carbonate in solution, and that I've added enough calcium carbonate so as much as can dissolve will. I might not have this high a concentration if I haven't left enough time or added enough calcium carbonate for it to reach saturation, for it to come to equilibrium.